Hello everybody. We're going to be continuing on our study of piecewise functions. If you remember from yesterday, these are just graphs that are cut up pieces of all the different types of shapes and functions that we've learned so far. So we have lots of options to choose from. You have the lines from Algebra 1, you have the absolute values and quadratics that we studied earlier in the year. We have polynomials like cubics and quartics and quintics and even factored form of polynomials where they bounce and cross. And let's see, after Christmas break we studied rational graphs and then square roots and cube roots, and we just finished a chapter on exponentials and logarithms. So we have a whole host of shapes to choose from, but the idea that is maybe a little bit more challenging in this target is how to limit those different ideas. And so that kind of comes from this last section of your piecewise function where it gives you domain restrictions. And so you just need to know how to read those and where to allow the graph to be drawn and where to restrict and cut the graph away. So for example, that bottom inequality says x has to be greater than or equal to -3. So that would be to the right or on potentially -3. If I go ahead and look at the top inequality, that says x is less than or equal to -4, so that would be on the left or on -4. So you have to kind of think along the number line in terms of where that is allowed to be built. So the left-hand portion versus the right-hand portion of those two areas. These connect and those connect. And so that should be a little bit of a review, and it's going to give you a chance to think ahead for this particular example. So let me get rid of my scribbles. Alright, if we go ahead and look at the top shape, that shape is an absolute value. So let's go ahead and let's write that in. It's always nice to identify things if we can. The absolute value has been reflected, and it has been moved left 8 and up 5. So if we go ahead and take our pen and follow left 8 up 5, we are going to be allowed to build in that location. So let me put a nice big dot here. Okay, and when I say build in that location, I'm referring to the restrictions, those domain restrictions. Anything less than or equal to -4, which we're clearly to the left of that. Now, afterwards, because I've been reflected, I need to go over 1 and down 1. So we'll put a dot here and here. And then we can go to the right, going over 1, down 1. And I'm keeping an eye on making sure that I'm building in the appropriate spot. So this would be the last dot. If I try to build at -3, -3 is not less than or equal to -4, and so it fails the conditional that's there. Afterwards, we can go ahead and connect those dots. This last one is a solid dot because we can equal -4. So we'll just go ahead and draw in our arrow. There is only one arrow, so I do not want you putting an arrow on this side because that kind of means that this graph continues in this direction, which would not be true. It stops. It has an end point, so be careful about that. The second shape, so maybe I will change colors here for this bottom set of instructions. This is a cubic. It is a cubic that has been moved left 1, and so if I take my pen and get my dots ready here, left 1 is going to be the center dot. So right there. And then after that center dot, cubics follow a pattern where it goes 1A, 7A, 19A. And so the A value up front is just an invisible 1. So we will travel over 1 and up 1, over 1 and up 7, which puts us at a total height of 8. 2 cubed is 8. Then we're going to go in the other direction. So left 1, down 1, and then left 1, down 7, which puts us at a total height of -8. -2 cubed is -8. And that is actually the last dot that I'm allowed to build. So there is nothing in this little gap between -3 and -4. Those two inequalities don't butt up against each other. So it is something where there is discontinuity, there is a gap that we will never be able to close. So it may take you a couple of tries to get that graph drawn in. A couple things I want to point out, so make sure, I'm allowed to kind of scooch this over a little bit, but try to be connecting to those point locations and don't overshoot them. So in my case, my curve went past this dot over here. Now on the right hand side, that is actually okay. I probably want to be careful that this is not angling back on itself. So we'll draw that over there. And it doesn't have to be the most perfect graph in the world, but as long as you have your points in the correct locations, that's really what I'm looking for. So we'll try to match the color. So it's light pink. Alright, so if this is our picture, is this particular final piecewise graph continuous or discontinuous? Well, because we were not allowed to connect -4 to -3, it will never be continuous. You have to have these values connect up in order for this to potentially be continuous, so we can circle discontinuous. The domain of this picture is really interesting. So because we only go up to -4 and there is a gap at -3, we have to report that down in our domain. So the x values go from -infinity to -4. We are allowed to stand on -4. And then they pick back up here at -3. We can stand on that location right there. And then we go to infinity. And next year, with pre-calculus and Mr. Van Bever, he will probably hook these two things together with a very large U. Okay, that U stands for union, and it unites the two areas together into one final area. So sorry, my U has a little bit of a squiggle there, but that's technically what you do when you have separate parts of a graph that need to get glued together into a final answer. I'm not going to take points off if you don't do that, but you do have to have the two different sections. Now our range, kind of interesting. If you think that -8 is the lowest this graph goes, you actually are not thinking far enough off your picture, because where does the rest of this absolute value travel? Well, if it travels straight down, you're going to surpass -8, and you're going to continue down towards -infinity. And so, because the right-hand side goes up forever and the left-hand side goes down forever, the range, the resulting range, is all reals. So I'll take my scratch work out of there, and we can put that answer here at the bottom pretty easily. So you got to train your eye to look at the overall picture and not just at prominent features. Be careful about that. Okay, traveling to the last question. This gets us a couple different shapes and some pretty good practice. All right, this is h of x. So good old Hank here has two equations, but they are some of the trickier equations that you might come across. So the first equation, if we look here, is a rational graph. If you don't remember rationals, they are double boomerangs, and it has been stretched by 2, so our spacing is going to be counting 2 away from that central location. And that's worth mentioning right now. The central location here is at the origin. We aren't moving it left or right, and we are not moving it up or down. So if I stay at the origin, typically when we did these pictures, we would put a star there. Okay? And after we did that, we would have an asymptote that extends horizontally and an asymptote, an asymptote that extends vertically. And I'll go ahead and I'll try to dash those. And weirdly enough, we don't end up really using part of this asymptote, which is not a feature that ever happened naturally, but because of the restrictions, so I hope you can kind of see my asymptotes, they're on the axes, but because of this domain restriction, saying x has to be less than 0, that means I need to be to the left of the origin, left of 0. So the half of the horizontal asymptote that's over on this side is pretty useless. And I actually probably am just going to erase it because it might get in the way of the other graph, and I don't want you to think that the other graph needs to, worry about avoiding this asymptote. Not true. The other graph doesn't care about that asymptote at all. It's not part of its graph. So if we go ahead and we think back about this 2, normally we would count 2 and 2, and we would put a curve up here, and then we would have a similar shape over on the opposite quadrant, if you will. But I'm not allowed to build over in this half because it's greater than 0, and so I will basically just end up having my dots in the lower left quadrant. So there will be a dot 2 away from the origin and 2 down from the origin, and we'll connect those with a nice curve. Now, a couple things to maybe consider. We are going to be able to put an arrow here at the bottom because that horizontal travel never surpasses 0 in the first place because there's an asymptote there. So it's going to continue to creep closer and closer and closer to 0, but we can't equal 0 anyway. So it looks fairly similar to what we discussed in that chapter. The left-hand arrow has 0 problems whatsoever. We would be able to put that because it's going away from 0 anyway. So that's the left-hand graph. Again, the part that was up here got cut away and tossed into the trash bin. So the second equation is down here. You have to recognize that this is an exponential shape. Exponentials also have asymptotes. So maybe I should really change colors for this, and that way we can tell our asymptotes apart. If I go ahead and look at the movements here, I'm going to be moving right 1 due to that number, and there is no up or down movement, so I can put a red star for my exponential here. Exponentials also have an asymptote that is flat, so that would be something where we can actually draw the asymptote right along that axis. So they seem to kind of have complemented each other. If this had been moved up, you may have an asymptote that is at a different height from the left-hand asymptote. That is totally a possibility. It just depends on the equations that we give you, up here. Alright, now that we have the groundwork laid, we need to go back and look at the initial value. You guys just took a test on this, so hopefully this is a little bit familiar. We're going to go ahead and graph a point 2 away. And then we are doubling due to the base, and so 2 away becomes 4 away, 4 away becomes 8 away, 8 away would become 16 away, and then over on the left, we got to be extra careful about this. We would be dividing by 2, and 2 divided by 2 makes 1. Now here's the catch. We are not actually allowed to build at 1 because I am not allowed to use an x value of 0. So that height is not actually going to be a solid height. It's going to be an erased or an open circle height. Okay? So if I go ahead and put my eraser in the middle and hollow that point out, now I am allowed to go ahead and draw the rest of the curve through those dots and through that open hole. It is also helpful that if you put these distances down here, then I know that you truly understand the pattern that's going on and those features about the shape. So if we look at this, we can evaluate a couple different locations. That's what part A is asking us for. Let me swap back to my normal purple color. H of -2. So you have to find the zone where that is true. Okay, the zone where that is true over here on the left. There's actually a pretty nice dot. So H of -2 is equal to a height of -1. All right. If I look for 0, H of 0. H of 0 has some issues. 0 isn't included in the left-hand equation, nor is it included in the right-hand equation. If you think about 0 as an x value right here in the center, there are no solid points. And so we would need to say that that is undefined because it doesn't satisfy any of the equations or inequalities. It's restricted for both domains. Then the third portion of this question says H of 2. H of 2 stands over here at this x value, and we need to look for its corresponding height, so 4. And again, these are talking about the coordinates 2, 4, or 0, there's not a point, or negative 2, negative 1 is the first example there. Okay? So just so you understand, that is something that comes up often on different types of tests, and you just need to be aware of the notation. Let's see. So part A, you could do that based off of the graph, which is kind of what we did. Part B is actually, we ended up doing that first. If you ever need to just do part A on its own, well, you decide, is this number going to fit into this equation? So you'll put it up here. Or does it fit into the lower equation based off of those restrictions? Okay, so negative 2, you put that in for x. 2 divided by negative 2 gives you that end result of negative 1. Just so you can see it both ways. All right, we are going to go ahead and fill out this key features table. And this should be hopefully pretty easy now that we have the picture in place. So the x-intercepts, if we look along that x-axis, there are none. And none is a perfectly fine answer for a lot of these features. The y-intercept, similarly, is none. We almost had a y-intercept at 0, 1, but due to the domain restrictions, that was not going to be a possibility. So none. The domain itself, so we moved that up the list. That's something you need to be very familiar with. So the x values go from negative infinity to 0. We are not allowed to touch 0. We will unite that with 0 to infinity. Okay, so we have the two halves, not the center. One thing you could do as well, since you notice the only number that's restricted is 0 itself, is you could say all reals, and then you could give a little comma and say x can't be 0. That's another way to write that. So the range, this is going to be a little trickier. The y values go down forever, so that's not really a problem I'm worrying about. But at 0, we have kind of this limitation due to the horizontal asymptote. And then there's a gap. So in between 0 and 1, nothing ever happens. We also need to be careful because 1, the height of 1, isn't a solid point. So this is going to be something where we go down forever and up to 0. We can't stand on 0 because 0 is an asymptote. You just approach it. We're going to unite that with 1 to infinity. And again, 1 does not have a bracket because it's not a solid point in that location. It's an open point. But otherwise, it does go up forever. Okay, the increasing and decreasing intervals. These will be good. So increasing intervals is going up a roller coaster. If I kind of go from left to right, I fall down a roller coaster, and then I pick up going up. So these are always measuring x values, amount of time. So it goes from 0 to infinity as increasing. And 0 does not get included, not because it's an open circle, but because at a point itself, you can't tell if you're increasing from a single point. So increasing and decreasing never gets a bracket. Single points, however, can be positive or negative with their height. So you just have to be careful about that feature. So the decreasing, still talking about x values, but everything prior to 0 would have been decreasing and going down a roller coaster. So that comes from negative infinity up to 0. And again, cannot include 0 because you can't increase or decrease at a point. The positive and negative intervals. Okay, this is based off of whether or not you are above or below the x-axis. So the first part is all below. So actually, if I wanted to say from negative infinity to 0, we have to include a parenthesis here because of the asymptote and because we're not allowed to actually equal 0. Then, after my first portion of the picture, 0 switches over to the exponential shape. 0 here is positive, but because it's an open circle, I have to include a parenthesis. If this had been colored in, so that green dot that's there, I would put from 0 to infinity. But because we are restricted from using 0 itself, and it's an open circle, 0 cannot be stood upon, so it needs to have a parenthesis, and then it goes forever. Okay, the rest of this shape will always be positive in heights. The end behavior, if you are a little rusty on this, This starts off saying as x travels, and I typically look towards negative infinity first. We're going to discuss the y values. And then we will look in the other direction as x travels towards positive infinity. What happens to the y values? So we're always just talking about heights and what happens to heights. Well, on the left-hand side, as we get further and further, the heights start to taper off. They actually reach a limited value of 0, and that is the horizontal asymptote. Okay, when we did this in the previous chapter, we would also talk about which side of 0 they were coming from. Coming from above versus coming from below are different actions. And so we would put from below. That's a lot to write, but hopefully you get the gist. On the right-hand side, we don't really need to worry about too much. The right-hand side, the heights increase and increase and increase faster and faster and faster due to being an exponential, and so the y values head towards infinity. Pretty simple. Asymptotes are really the tricky part with end behaviors. And then the last question that we're asking, is this a function? Okay, kind of a weird question because these are called piecewise functions, but sometimes people might have you build things that would maybe not be a function. And that's just a piecewise graph. This is a function, and that is because no x values produce more than one y value, or you could say each x value corresponds to at most one unique y value. There is an x value at 0 itself, x equals 0, that doesn't do anything. It's a big and we actually saw that up here. And that's fine. You can have x values that don't produce things or x values that produce imaginary numbers. You're just never allowed to have an x value that produces too many y values. That's what breaks the rules of being a function. Okay, so the last portion of this video, if you've gotten that all down, is just to get you guys thinking about our project that will be coming up. I love this project. This is something that kids really start to use their imagination, and they create some wonderful and awesome ideas. So down at the bottom, you can kind of see this whole picture of New York and all sorts of architecture. This was created in Desmos, which is what you guys will do, by writing equations and cutting them up, restricting their domain. And you could start to see some of the shapes that we've learned about this year. So maybe down here, these shapes, to me, look kind of like logarithms. Either logarithms or maybe square root shapes. There is actually a shape up here we haven't discussed. It would be a sine wave or a cosine wave. We have lots of lines. Trying to think, this guy might be an absolute value. And so it's kind of neat to have like a scavenger hunt and look for all the different types of shapes. Maybe over here that's a quadratic. But this would take you a long time to set up. Having some of those limitations, you're going to have to cut them above and below, or you're going to have to cut them on the left and the right. That's pretty tedious stuff. It's also worth noting the scale of this picture goes up to 1,500, and it even goes further than that in the horizontal direction, out to 3,000. But boy, what a cool picture. They put the Statue of Liberty in here and everything. So that's something that people in the past have made that, not in my class, but out in the real world. And I think that's really cool. If you flip to the next page, here's another couple of really good examples. And I got these from Desmos themselves. Every year they have a little bit of an art contest, and so these were some of the submissions that got entered into that. And kids have won in the past. They have different age ranges. Kids have won in the past, and they have created like really incredible things that I don't even know how to make. So you got a picture of a hand and a light bulb, some inspiration. You can see, now that I'm including a snapshot of Desmos itself, that there are about 400 different equations or pieces to this graph. The folders are kind of hiding all of them, so you're able to group them into different categories, and you can turn them on and off. So these are off, but these are turned on, and you actually see them out here in the picture. Well, that's cool. And then the last picture of the jellyfish, I wasn't able to show this, obviously, because it's on paper, but the bubbles would move and they would like float around a little bit, and there was some animation to that, which is totally possible if you use a slider, but I just thought that was awesome. And you can see that maybe they aren't using as many equations on that picture. It goes into the 150s. But that's still a lot, and that's kind of what it takes to craft something that you have in your head, you have thought about. So just a little bit of inspiration. Really the rest of today is a chance for you guys to work on the homework and be looking at those problems and trying to take them apart and put them back together under one unique piecewise graph. So let me know if you have questions. Be happy to help, and we'll keep working on this here for the upcoming days. Thanks for watching, guys. I hope the video helped, and we'll see you guys next time. Take care.